All right. So today we're gonna look at 2018 AP Calculus BC free response questions. So this is the year that I took AP Calculus BC test. Now I looked through the questions and none of them ring a bell. So I'm thinking that it's possible that maybe, I know that there's different like sections or different like forms for the tests. So I don't think these are exactly the questions that I had. But I'm guessing, other people that I knew would have taken this at the same time as me. So I'm just going to go through this. I know it's AP season, so I figured why not. So we're going to start off. So the first section, we have 30 minutes, so it's on my end, it is 10:27. So I'll have until 10:57. And there is a graphing calculator. So I don't have a way of showing, but I have a graphing calculator. Okay, so we have a rate function for people entering a line for an escalator. And so when people get on the escalator, they exit the line at a constant rate. Okay, so I'm assuming that A is just asking, for us to integrate R of t from 0 to 300. That's how many people would enter over that time interval. So we'll just go ahead and do that. So we have 44 t over 100 cubed 1 minus t over 300 to the 7th. Now I was going to do this explicitly, but I recall that thankfully graphing calculators have numerical integration capabilities. So that is exactly what I'm going to do. I'm pretty sure this is not intended to be done by hand. So I'm just gonna plug this integral right into my calculator, and I get 270. So that's how many people join the line. Now it says there are always people in line. How many people are in line at t equals 300? So people are exiting at a rate of 0.7 person per second, meaning that, so we would have 20 initial plus 270 people join, and then minus 0.7 times 300. Now, never mind, I was going to say that's a fractional amount, but I am just, tired. So just do the calculations. That is 80 people. Okay. Okay, so now as there are 80 people, where is the first time? So it will take, so t will equal 300. So after 300 seconds, no one is joining the line anymore, so you only have the 80 people that are there. and then those 80 people are going to leave the line at the rate of 0.7 people per second. Yeah, so the units here cancel, and this is going to give us 414.286 seconds. I remember the calculus teacher at my school said something about how many decimal places that they typically wanted, and I forgot the rule for that, but I'm just gonna do 3. At what t is the line of minimum? Alright, so I'm just gonna bring this to the next page. So, okay, so let's think. So, our number of people, this is part D, our number of people starts out as 20, and then we have the integral from 0 to t of r of x dx. I'm using a different variable here for the integral. Minus well, no. I think I have to set this up as a differential equation. So n prime of t, so what's the rate of change? Yeah, and then I would have to set that equal to 0. So the change of people is r of t minus 0.7 n of t. I believe that is correct. So the change in my number of people is how many people are joining, and then minus how many people are, or the rate at which people are leaving. No. I think it's just minus 0.7, because this is already a rate. Yeah, I would have to multiply it by time for that to make sense. So this is the change. And so when this is equal to 0 is when you're going to have an extreme value. So r of t equals 44 t, what was it? T over 100 cubed is 1 minus t over 300 to the 7th is equal to 0.7. Now I'm imagining that I just have to solve this. So graphing calculators have a numeric solver. So I'm just gonna do that. Cubed 1 minus x over 300, oops, x over 300 to the 7th, and then this is equal to 0.7. Okay. I get that t is equal to 166.575 seconds. Now, how would we know that this is actually a minimum and not a maximum? Oh, yeah, so we should check that that is a minimum and not a maximum. So the way I could think, the first way I could think is to check the second derivative. So the second derivative is just going to be the derivative of t. And so that's going to be, well, there is a numerical derivative. So what I'm going to do is I'm just going to slap that formula in. I'm just going to slap R of t in so when I plug in this value, x equals 166.575, I get that, so r prime of 166.575 equals negative 0.024, meaning that this is in fact this is a max. Right, so whenever you have a second derivative which is negative, that means that you're at a local maximum. Therefore, the minimum must be at, or so let me think. So this numeric solver, I'm wondering if there could have been other solutions that it didn't show me. So let's graph it first. So I'm graphing the function. Let's do my window. I want to go from 0 to 300 exactly. And then I can do zoom fit. So it will fit the curve to that x. So it is looking like there are two solutions. So let me check the other solution. So let me go back to my numeric solver, and I will set the bounds differently. So the bound will be from 0 to 100. So I guess or t equals 33.013. At this point, the derivative of r of t gives us 33.013. R prime of 33.013 equals 0.045. So this is a local minimum. And therefore, what we need to do is say integrate r of t and check that this is lower than 20. So 33.013. So n of 33.013 is going to be 20 plus the integral from 0 to 33.013 r of t dt plus or minus 0.7 times 33.013. So plus 20 minus 0.7 times 33.013. And this gives me 3.803, which is less than 20. So So t equals 33.013 seconds is where there a minimum number Okay, so the strategy here was, we have to find an extreme value of the number of people, which means that the derivative is equal to 0, or we have to check the endpoints as well, which is, why. So if we set n prime equal to 0, we end up having to solve r of t equaling 0.7. This gave two solutions. One was a local maximum and one was a local minimum, which we checked by taking the second derivative. And then we had to actually check that this local minimum would be less than either of the endpoints, the smaller one being 20, and it was. So this is the minimum. Okay, so that was question 1. We have we have 15 minutes left, so we're pretty much on time, because I believe it's just the 2 questions for 30 minutes, so we're exactly on time. Now, of course, I have to stop and explain things. So, researchers on a boat are investigating plankton cells in a sea at a depth of h meters. The density is set millions of cells, so this is going to be important to take note of. Millions of cells per cubic meter. So m cells per meters cubed. I'm just going to write that to remind myself the units, because units tend to be kind of tricky. So here's the density, and it's modeled by f of h for h bigger than 30, so the depth. So we're going from here to 0, and we're going down. Okay, so the first part is to find p prime of 25, and honestly, again, I'm just going to use the numeric derivative capabilities of my graphing calculator, because there's absolutely no reason not to. They let you use a calculator, you might as well not waste time taking the derivative and then plugging in 25. There's just no point. So p prime of 25 is equal to negative 1.179. So what does this mean? So h is given in meters, so this means a depth 25 meters. The density decreasing by 1.179 million cells per meter cubed per meter. Okay. Now we consider a vertical column with horizontal cross sections of constant area 3 square meters. To the nearest million, how many plankton cells are in this column of water? So, okay, so let's think. So here we have some column, just going from 0 to 30, And, we split it up into tiny cross sections. So the volume of one of these cross sections is going to be 3 meters squared times the little strip length of the strip, so 3dh. And then the volume, so that's the volume that that strip occupies, and then the number of cells is going to be P of H. Of course, that's going to be in millions of cells per cubic meter. The 3 is meters squared. The dH is in meters. So this is going to give us a number in millions of cells. And it wants us to give to the nearest million. So essentially just rounding this to the nearest integer would suffice. So I'm now going to integrate that. So 3 times 0.2 times x squared times e to the minus 0.0025 x squared. Let me make sure I got the right number of zeros there. So this gives, well, to the nearest million is 1,675 million cells. Okay. All right, on to part C. We want, okay, so there is a function u such that f is bounded between 0 and u. So f is the density past 30 meters. And the integral of u of h from 30 to infinity is 105. So essentially what that means is that the integral of f of h is gonna, in that interval, is gonna be less than or equal to 105, meaning that there are at most 105 million cells of plankton past 30 meters in that column, or in a column of unit area cross section. The column of meters. Write an expression. Okay, so n is going to be, so first is going to be the integral from 0 to 30 of 3p of h dh. So that's going to give us the first amount. And then from there, we go from 30 to the new depth. And again, we have strips of volume 3dh. And those have density of f of h, which is, I'm presuming, this has the same units, and so the units here check out. So this is the expression. And 30. So now this integral here is less than or equal to the integral if we increase the bound to infinity, because this is non-negative, right? It's a physical quantity, so or it's a quantity of density. Density could not be negative. So then we replace this here, and then that is less than or equal to, if I take out the 3, and then this is going to be the the integral from 30 to infinity of u of h dh. And so this is equal to 3 times 105, which is 315. Thus, n is less than or equal to 1676. Since I rounded down here, the answer to this integral was like 1675.4. So I'm just gonna round it up here. And so this upper bound is equal to 1991, and this is less than or equal to 2000. Okay. So now part D. So we have 5 minutes left, but we should have good enough time. The boat is moving on the surface of the sea. Time t greater than 0. Okay, so this has pretty much nothing to do with the density info, and this is just arc length of a parametric curve, and so the distance is going to be the integral from 0 to 1 of the square root of x prime of t squared plus y prime of t squared dt, right? This is the arc length formula. And I'm just gonna plug in x prime of t and y prime of t and use numerical integrator because I don't see a way that is a very nice integral to do by hand. And again, it's the calculator section of the FRQs, so might as well make the most of it. Oops. So the sine of 5x squared, and then plus 880 squared, cosine of 6x squared, I'm hoping that when it says total distance, it does mean arc length and not just net distance. Like, interpreting this as, well, no, you wouldn't, they haven't, I mean, I guess so you could calculate the initial and final. No, but they don't give you initial. Yeah, so you wouldn't be able to compute that. So this is 7.456 meters. Oops, that was really ugly. I'm so sorry. Okay, so that is that, with 2 seconds to spare. Alright, so now we're on to part B. No calculator is allowed, so I am putting away my calculator. Alright. Honestly, the non-calculator part's my favorite. The graph of the continuous function g, the derivative function f, is shown above. Okay. If f of 1 equals 3, what is f of negative 5? So what this is saying is that f prime of x equals g of x. So if we integrate from -5 to 1 of g of x dx, that is going to be equal to f of 1 minus f of minus 5, which is going to be 3 minus a, where a is the answer that we want. Of course, I should... Nah, I'm just going to save space and do that up here. And so the integral is just going to be the sums of these areas. So here we have what looks like a 3 by 3 square, so that's going to be 9. Here we have a 1 by 3 right triangle, so that's going to be 3 halves. And then here we have a 2 by 1 right triangle, so that's going to be 1. And so this integral is equal to, well, we have to make sure that we take into account the signs of these areas, right? So the 1 will be positive, but the 9 and 3 halves will be negative, so minus 9 and minus 3 halves. Now this is negative 19 over 2. Let me just double check in my head that that's right. Yep. And so a, which is the answer, just going to write this over here, is 3 plus 19 over 2, so 25 over 2. Just going to make that more legible. Okay. Now evaluate the integral from 1 to 6 of g of x. So the first part of this, so from 1 to 3, is just the square. So we get 4 plus, and then starting at 3, right, we can integrate this as the parabola. Okay, so this is going to be the same as, so 4 plus 2 times the integral of, I'm just going to shift everything over. Of course, this is times 2, so yeah, so that makes sense. Of x squared dx. So this is 4 plus 2 times x cubed over 3, so 8 thirds minus negative 1/3, or yeah, minus negative 1/3, so plus a third. So that's going to give us 9 over 3, which is 3. So 4 plus 2 times 3 is 4 plus 6, which is 10. Okie dokie. For negative, so on this, pretty much just what's shown on the graph, on what open intervals is f both increasing and concave up? So f increasing, concave up is the same as g positive and increasing, right? So obviously this negative half is completely scrapped. Now here on this first piece, right, from 0 to 1, it is positive and increasing. So 0 to 1, and then from 4 to 6, it is positive and increasing. So these are the open intervals. Okay. Now find the x-coordinate of each point of inflection. So again, f prime, double prime changes sign exactly when g prime changes sign. Oops, can't spell today. So we just look at the graph. So here g prime is 0, and then it goes positive, and then it goes 0, and then it goes positive, and then it goes 0, and then it goes negative. So all these points where it's going to 0, So on these pieces where g is constant, that means f is linear. So I don't think that counts as an inflection point, because it's not changing sign. It's only going from 0 to positive or negative. So the only inflection point is here at x equals 4, as g prime goes minus to positive. So I believe that's the only inflection point. I don't think going from 0 to some sign to 0, I don't think those count as inflection points. Okay, unless yeah, I'm just gonna stick with that. That's my belief in the word inflection point. All right. Oh, I forgot to check. Okay, so we had 1 hour for this, and I believe that we finished the last one at 10:55. So until 11:55. It's currently 11:02, so I have 53 minutes. So we used 7 minutes for that last question. Okay. The height of a tree at time t is given by a twice differentiable function h. So we're given some values of h. Estimate h prime of 6. Okay, so this is m and this is years. Okay, so I guess really the only thing that we have to get an estimate is the rate of change from 5 to 7. That's all we really have. So h prime of 6 is approximately the change in h over the change in time. So that's going to give us 5/2. And this is 2.5 meters per year. So at 6 years, the height is increasing at 2.5 meters per year. Okay. Now we have, I'm gonna start writing over down here. Explain why there must be at least one time t from 2 to 10 where h prime of t equals 2. So I believe in order to do this, we have to find some point, some interval where the average rate of change is 2. And after just some guessing and checking, I guess, we see that over the span from 3 to 5 years, so notice that h of 5 minus h of 3 over 5 minus 3, which is 6 minus 2 over 2, which is 2. So by the mean value theorem, there is some t, and in particular we know it must be between 3 and 5, where h prime of t is equal to 2. Okay. Use a trapezoidal sum where with the 4 subintervals indicated by the data in the table to approximate the average height. Okay, so we have to find the average value of h. So average of h of t is going to be 1 over 10 minus 2 times the integral from 2 to 10 of h of t dt. Okay, so so this is going to be 1/8, and then we have to approximate the integral using the trapezoidal sum. So the trapezoidal sum is where we essentially, let's graph this. So at t equals 2, so let's call this 2 and let's call this 10. We have 3. What's in the middle here? 6, which isn't an endpoint, so let's call this like 5 and 7. Should be good enough. So we go 1.5, we go 2, then we go 6, then 11, 15, right? So the idea is that, right, in order to integrate this, we can approximate the curve by line segments and add up these 4 trapezoid areas. Okay, so I'm just going to do this up here since it's easier. I have the data with me. So here the change, so we have to take the average of the heights, so 3.5 over 2, and then times the change in t, which is just 1, so we have 3.5 over 2. And then we have the average of 2 and 6 is 4, times the change in t is 2, so 8. Then here, the average here is 17 halves, and then times the change in t, so that. And then here, the average between 11 and 15 is 13, times the change in t is 3, so 39. Okay, so 3.5, that's going to be 1.75, and then 8 and 30, let's see, so this is going to be 24 plus 40, so 65.75. And I guess I can estimate this to the best of my ability. So this is going to be, it's going to be closer to 8.25, right? So we have 8 plus 1.75 over 8. So that's going to be close to 2 over 8, which is 0.25. But it would be a lot bigger than 0.125. So let's just say 8.2 meters. That should be good enough. Alright. The height of the tree can also be modeled by the function g, which is given explicitly when the tree is 50 meters tall. Okay, so x is the diameter, so instead of... Okay, so I think this is going to be like a related rates problem. So this is height, so when height is 50, diameter is increasing at... Okay, so what we have to do is take d dt g of x, which is going to be g prime of x dx dt, and we know, well, I'm just going to compute this out first. So g prime of x is going to be 100 over 1 plus x minus 100x over 1 plus x squared. So if I multiply this, I get 1 plus x squared. So 100x, so this is going to be, and then this is multiplied by 0.03 meters per year. This is, right, so this is 3 over 1 plus x squared. The units should be meters per year, so I'm assuming g prime of x is unitless. That makes sense. So now we have to find out what x is. So we have 50 equals 100x over 1 plus x implies 50 equals 50x, which implies x equals 1. So the rate of change is 0.75 meters per year. So pretty interesting problem overall. Alright, we have, how long? Till 11:55, so we've got 40 minutes to go. 41, but should be done. Let's see, there's 2 more problems. Yes, we should be done with plenty enough time. Alright. So here we have polar graphs. This is going to be hopefully not embarrassing. So we're given the angles of intersection here. Of course, we know the radius of intersection as well. Alright, so I'm just going to do part A up here. So let R be the shaded region. Okay, so let's think about this. I'm going to be spinning theta in the counterclockwise direction, which of course is the natural direction to go, from theta over, or from pi over 3 to 5 pi over 3. And then, let's see if I remember how to do this correctly. So, if I recall correctly, we would do something like 1/2 r squared d theta. And I think since the curves are nice in this region, what I can do is say I just subtract. I don't want to do r1 minus r2 quantity squared, but I do r1 squared minus r2 squared. So what I'm going to do is integrate from pi over 3 to 5 pi over 3, and then I have 1/2, and then I have 4 squared minus quantity 3 plus 2 cosine squared, or just cosine theta squared d theta. And then it doesn't say to compute, it just says write an expression, so that should be good. Now, of course, this first, if I wanted to, I could, I mean, this should be good enough. I think what you can do is, since this is a circle centered at the origin, I mean, we know that part of this area is just going to be just like a circle sector area that we can find easily. And of course, that corresponds to just integrating a constant times d theta. But I mean, it just says write an expression, so this should be good enough. Find the slope of the line tangent to the graph of at pi equals at theta equals pi over 2. I keep mixing up. So find the slope of the line tangent here. Okay. So how would I go about that? Of course, I think what I can do is say, but is that necessary? So what I can do is say x equals r cosine theta and y equals r sine theta, and then I can do I can compute dy dx by doing dy dt, or I guess dy d theta, divided by dx d theta. I think that's the intended route, so y equals 3 sine theta. So r is, of course, this r right here. So 3 sine theta plus sine of 2 theta. Get that nice little simplification there. And so y prime is going to be 3 cosine theta plus 2 cosine 2 theta. And so at theta equals pi over 2, cosine's going to vanish, and the cosine of 2 theta is going to give us -2. Now this makes sense because if we're following the curve, our y is decreasing. We should also get a negative value for x prime. So x is 3 cosine theta plus 2 cosine squared theta. Take a derivative, and we get -3 sine theta. -2 sine of 2 theta. Because you drop the 2, but then you're going to have a cosine theta and a sine theta, so that all becomes sine 2 theta. And then the sine theta that comes out of the cosine is actually a minus sine theta. But anyway, of course, now we just plug in the value of theta. This sine will disappear because sine of pi is 0, and we just get -3 times sine of pi over 2, which is sine of just 1. So x prime is -3, and so the slope is -2 over -3, which is 2/3. And I don't know, that looks okay. All right, now on to part C. Particle moves along the portion of all right, so we're moving from here. We're moving from here to here, okay? Traveling along this curve. The distance between the particle and the origin increases at a constant rate of 3 units per second. Find the rate at which the angle theta changes with respect to time. Well, so the distance between the particle and the origin is just by definition r. So that tells us that dr dt equals 3. And we also know it's equal to the derivative of this. So this 3 goes away. And then we get minus 2 sine theta d theta dt. Okay, and we get an answer that I was expecting. So at theta equals pi over 3, we get minus 2 sine of pi over 3 d theta dt. And sine of pi over 3, as this triangle here indicates, is square root of 3 over 2. Yeah, so this is minus square root of 3 d theta dt, implying d theta dt equals minus square root of 3 radians per second. All right, and that makes sense. I was confused at first because I thought, you know, when it indicated this portion, I thought theta would be increasing, but of course this answer makes sense. It has to be theta is decreasing, because for r to be increasing, we have to be moving along this portion, right? Because of course we have the circle to compare to. The circle is a constant r. Here the graph is at a lesser r value, and then they intersect, and then here it's at a greater r value. So for r to be increasing, you have to be going along this way along the curve, which corresponds to moving negative in the theta direction. So that looks good. All right, last question. All right. So they give us the Maclaurin series for ln of 1 plus x. They ask us to find the first 4 non-zero terms. All right, so A, I'm just going to do it up here again, just to save space, I guess. So what we can do is just plug in, right, we can use ln of 1 plus x, but we're substituting x over 3. So we have to make sure to put in x over 3 everywhere there is an x. So it's first 4 non-zero terms, so we can just do it like this. 1/4 x over 3 to the 4th. So this is going to be x squared over 3 minus x cubed over 18 plus x to the 4th over 81 minus x to the 5th over 81 times 4 is 324. So that's good. Well, I shouldn't put a period there, but I should put that there are more terms. But those are the 4 terms that they want. Determine the interval of convergence of the Maclaurin series. So I don't think that multiplying by this x here is going to affect anything. Now I'm fairly sure that the interval of convergence for this is -1 to 1, but of course they don't tell you that, so I'm assuming we just have to do the work for that. So let's just quickly write that f of x is the sum as n goes from, let's go 2 to infinity, of, let's say, well, so we have x to the n, we have -1 to the n, we have n minus 1, and we have let's put a 3 here and a 3 to the n here. Well, I guess let's just say 3 to the n minus 1, why not? So that should be good. So essentially what we have to do here is take the limit, or take the ratio of consecutive terms. So, right, so we have x n plus 1 times -1 n plus 1 over n 3 to the n. This is divided by x to the n minus 1 to the n over n minus 1. 3 to the n minus 1. Okay. So this is absolute value. We can drop the negatives. We get an absolute value of x over 3 times n minus 1 over n. So as n goes to infinity, the ratio tends to x over 3. So the radius of convergence is 3 by the ratio test, right? The ratio test says for this series to converge, this ratio, or the limit of the ratio, should be less than 1. And so for the ratio, so for this to be less than 1, that means x is between -3 and 3. Now we have to check endpoints. Now at x equals 3, the series f of x is, let's see, minus 1 over n, 3 times that over n minus 1, which converges by the alternating series test. Of course, this is the alternating harmonic series, and this is going to approach 3 times the natural log of 2, as we would expect. At x equals -3, f of x is the sum from n equals 2 to infinity of 3 over n minus 1, which diverges as it is a p-series with p equal to 1, right? Another way of saying this is that it's the harmonic series. It is, right, it is where p-series start to diverge. Okay. So, thus, the interval of convergence is hard cap, soft cap on -3, and then hard cap on 3. Okay. Last part, 22 minutes left, so we made good time. Let P4 be the 4th degree Taylor polynomial for f about x equals 0. Use the alternating series error bound to find an upper bound for P4 of 2 minus f of 2. So, excuse me. So P4 of x, as we've calculated, is x squared over 3 minus x cubed over 18 plus x to the 4th over 81. And then P4 of x minus f of x is going to be, let's think, x to the 5th, you get a minus, yeah, so x to the 5th over 324, and then minus the other terms, right? So, I'm pretty sure that the alternating series error test says that that the bound for this is going to be the absolute value of this next term. So I'm not completely sure on that, but you know, I think we've made, you know, I'm pretty confident in the rest of the test, and you know, you can make not a 100 and get a 5 on the test, right? I got a 5 on the test. So, you know, I'm not super, this is like the only answer on these free responses that I'm not not sure on, but I believe that this would be 2 to the 5th over 324. And of course this is, after canceling out the 4 in the numerator and denominator, this is 8 over 81. So there you have it. That is my attempt at the 2018 AP Calculus BC free response questions. Again, these are not the questions that I had on the test. I mean, it's not like I remember the questions, but I don't remember any of these questions, and I think I would. But, you know, they're pretty standard. Like, I remember having sort of a, you know, there's going to be a part where you have to do numerical integration. There's always, the last question is always, or as I've, in my practice, I remember, usually, I guess not always, but usually there's a question about Maclaurin and Taylor series. I don't recall a polar integral or polar section, but or maybe just parametrics in general. Be prepared for that. Definitely one of these graph questions. These like rate function questions, those are usually on there. So pretty standard selection of topics on these questions. So I hope this video helps for anyone preparing. I know that these questions already have videos on them, but regardless, I hope this helps someone. So yeah.